Hello and welcome to this webinar hosted by the Nordic Institute of Dental Materials. I am Amund Ruud. I'm a scientist here working on ceramics.
My name is Freya Sofia Andersen, and I'm an engineer here at NIOM. We will be co-hosting this webinar about zirconia in dentistry.
Zirconia is today one of the most commonly used materials within dentistry. It has gained its popularity within the last 10 to 20 years, and the reason for this is mainly due to its high mechanical strength as well as its relatively good optical properties. In addition to its use within dentistry, it is also used within research on solid-state electrolytes, and it's also used as thermal barrier layers in furnaces. Perhaps the biggest reason for the high strength of zirconia is the tetragonal to monoclinic phase transition. Starting with the tetragonal phase, this is what we achieve when we use some yttria as a dopant within zirconia, stabilizing this phase. The tetragonal structure is recognized due to its 90 degrees angles between all phases. We have the A-axis equal B-axis with a slightly longer C-axis. When we transition to the monoclinic structure, we get a structure which is slightly tilted, and the sides of A and B are not anymore equal. This transition is called the martensitic phase transformation. It has also other names such as the martensitic toughening mechanism, as well as others. This is just the name of the transformation, and it's recognized due to no atoms changing when going through the phase transformation. In this phase transformation, the volume changes slightly. It has an increase of about 7%, and this volume expansion is very important, improving the mechanical properties of the zirconia. On the right-hand side, we have a description of a crack propagating through a zirconia material. Around the crack, there is a phase transformation where the tetragonal phase goes to the monoclinic phase. The volume expansion can then stop and arrest the crack, and in theory, this improves the material's mechanical properties significantly. When investigating yttria-stabilized zirconia, there are also other phases to consider. In the shaded blue area, we are within the region which is commonly used within dentistry. This is 3 to 5 mol% Y2O3, although in this figure it's represented as YO 1.5. Common sintering temperature is around 1500 degrees, although this varies somewhat depending on the yttria concentration. Typically, at higher yttria concentrations, we sinter at a slightly lower temperature, such as 1450, whereas for the 3 yttria mol%, we sinter at 1500 degrees. Based on this phase diagram, we not only expect to get some tetragonal phase, but we also expect to get some cubic phase, as we are in the two-component region between these two phases. In more recent research, there has also been suggestions that in addition to the tetragonal and cubic phase, we have several other tetragonal phases, here denoted as T prime and T double prime. The T double prime is often not discussed. This is partly due to its difficulty in being evaluated, but studies such as synchrotron studies have reported this phase as also being relevant. When working with zirconia, we are typically working on a compromise between the optical properties and the mechanical properties. The highest mechanical properties we observe for the 3 mol% yttria, and the highest optical properties we observe for the 5% yttria. It is important to try and optimize the yttria content with respect to these two properties, and often we have to do some compromises depending on which is the most important, and what can we settle on?
More recently, what's known as multi-layer zirconia systems have been introduced to the market to further optimize dental zirconia. These can be divided into two main types, color graded and strength graded. In color graded, here shown to the left, the zirconia blank shows a gradient in color from the addition of varying amounts of pigments. The aim of the design is to mimic the natural color gradient found in teeth, so that the resulting dental restoration is most opaque in the gingival region and gets increasingly lighter and more translucent towards the incisal area. In this case, the amount of yttria is constant throughout the material. Contrary to this, the second type of multilayer zirconia, the strength graded, has a varying amount of yttria throughout the material. For example, as shown in the figure to the right, the blank may start at one end with a layer of 3Y zirconia with 3 mol% yttria, and gradually increase in layers up to 5 mol% yttria in zirconia. Due to the different concentrations of yttria, the strength of the material also varies between the layers, decreasing from 3Y to 5Y in this case. And this results in a restoration with the highest strength in the gingival region and decreasing strength, but thus also higher translucency towards the incisal area. This design thereby takes advantage of or makes the most of the different types of zirconia in one and the same restoration. It's worth noting that the strength graded zirconia often also is color graded at the same time. Recently, we conducted a study here at NIOM where we investigated a selection of multi-layer zirconias currently available on the market. And the first five materials used in the study, shown in the graph, are color graded, while the last is both color graded and strength graded. The specimens for testing were prepared from the cross-section of the zirconia blank so that all layers were included in one single specimen. The figure to the left shows the measured translucency parameter for each material, and the translucency parameter is just a measure of translucency that's based on the color difference of the material over white and black backgrounds. The results that we saw are generally as expected based on the material's respective yttria concentrations, with materials having a higher yttria content showing higher translucency, and vice versa. We also measured the color of the materials, meaning the LAB values according to the CIE LAB color space. What's interesting to note here is that although all the products were purchased in the same color, according to the Vita Shade Guide, which was C2 in this case, they didn't necessarily have the exact same LAB values. So for example, shown to the right here, the B value, which represents the blue-yellow component of the color, is higher for the two products from Dental Direct, shown to the left in the graph. So this means that these products were slightly more yellow compared to the other four, and that was something that in fact could be seen with the naked eye as well. Finally, in addition to yttria content and shade of the restoration, the thickness, glazing procedure, and chosen cement for cementation are among the other factors that will have an effect on the translucency of the final product. We also measured in the study the flexural strength of the materials using a ball on 3 balls test setup. And the results are mostly in agreement with the values reported by the manufacturers. Although slight variations in our measured values compared to the values given by the manufacturers may, for example, occur due to differences in test setup and specimen geometries. One exception to this was that the flexural strength of Curaray's Katana STML and UTML were similar in our case, contrary to the manufacturer who reports a higher value for STML. The higher value for STML is also expected due to its lower yttria content. Equivalently, in theory, we might have expected similar flexural strength values for Dental Direct's Cube 1 multilayer and Curaray's Katana STML, as they have the same level of yttria, although our values are in agreement with that reported by the manufacturers. As of now, we can only speculate as to why this is the case, but slight variations in yttria content, particle size of the starting material, binder content, coloring strategies, and the thickness of each layer may all be contributing factors.
In a recently published project, we evaluated 3, 4, and 5 mole % yttria contents within Zirconia. We replicated the pressing and pre-sintering procedures commonly done by dental manufacturers. We sectioned the samples for investigation and sintered the samples. The main objective of the project was to evaluate the effect of uncertainty of your sintering furnace. There have been studies reporting that dental laboratories can have up to 5% uncertainty within their sintering temperatures, meaning that if you, for example, sinter at 1500 degrees, the actual furnace temperature can vary with 5%. So for instance, for 3 mole % yttria, it can be for 1550 or 1450 degrees centigrade. The question then was, how does this affect phase composition, mechanical properties, and optical properties of the final products? As previously mentioned, the most commonly used theory regarding the crystal phase composition is that we usually get some ratio between the tetragonal and the cubic phase. However, in this work, we discussed the importance of also including the tetragonal prime phase. Here we look at an example when we include the tetragonal prime phase as well as the tetragonal and the cubic model in a rhythmic refinement. The cubic phase is very minor and has a relatively small crystallite size. However, the tetragonal and tetragonal prime model is more relevant. For the 5Y material, we also see the effects of this. The tetragonal model is now not as high, the amount is not as high as for the tetragonal prime model, but it's still there. Differentiating between the tetragonal prime phase and the cubic phase, one often see that the tetragonal prime phase is evaluated as the cubic phase. However, here it's quite clear that you have a double reflection both for the tetragonal model and the tetragonal prime model, for instance, in the range between 70 and 80 degrees to theta. Also, as a quick comparison, we see if we use the cubic model, which is shown in the lower panels, that although it might be considered somewhat of a fit, we see that the fit is improved considerably when we include the tetragonal prime model, which accounts for the double reflections from both the tetragonal phases. Here we show our results from the 3 to 5 yttria mole % in Zirconia. To the left, we have two different 3Y materials. The difference between these two materials is that they have 5% and 3% binder. For the rest of the materials, we have 3% binder. The benefit of a higher binder content is that you can mill more complex shapes. However, we'll see later on that this reduces the mechanical properties somewhat. We here observe the phase fractions between the tetragonal prime, and the cubic phase, and we then see also the variations when you increase the yttria content, that you generally get less of the tetragonal phase and more of the tetragonal prime phase. We also see that this is somewhat affected by the sintering temperature, which was the recommended 5% below and 5% above the recommended sintering temperature. As mentioned, how would this affect the optical properties? We see that for the lower temperatures, for the 3Y materials, that the transmittance is significantly reduced. However, for the recommended and the sintering temperature above the recommended temperature, the effect is very small. The 4Y material is has generally a higher transmittance and with a relatively low variation due to sintering temperature. Whereas for the 5Y material, we see that if you sinter at the too low temperature, the optical properties or the transmittance in this case is quite significantly reduced, whereas if you have a higher sintering temperature, the effect is not as severe. We also see, when we compare to the phase fraction, that, for instance, in the case of phi y, we reduce the amount of the cubic phase, we increase the amount of the tetragonal prime phase, and we reduce the amount of the tetragonal phase with increasing sintering temperature. Commonly in the literature, one say that the higher translucency or the transmittance of the 5Y material is due to the higher amount of cubic phase, whereas in our case, this is not what we see. Here it's more related to the increased amount of tetragonal prime phase. However, this is not surprising, as often it seems that the tetragonal prime phase is confused with the cubic phase in literature. Considering the transmittance properties of zirconia, there are many aspects to be considered. Of course, we have the phase composition, where the cubic phase is a so-called non-birefringent crystal phase, reducing the amount of scattering, whereas in the tetragonal phases we have some birefringence, which can increase the amount of scattering somewhat. In addition to this, of course, light will reflect off the surface of the sample. We can have scattering from grain boundaries. We can have scattering from pores. We can have reflection within the material. And then finally, of course, some light will make it through, making it either translucent or fully transparent. Of course, in the case of zirconia, it is translucent. Comparing the crystallite size of the different yttria concentrations and the different sintering temperatures, it seems that if you, for instance, look at the 3YC panel, that the crystallite size is somewhat comparable to the 5YD panel. We also see that the transmittance of these two materials are somewhat comparable. Although the phase composition is important for the transmittance, it is definitely also important to evaluate the grain size here. We also see that when we increase the sintering temperature for the 5Y, we have a somewhat larger grain size, and we have higher transmittance. However, from the recommended sintering temperature to the 5% above the recommended sintering temperature, although the grains are quite a lot larger, the effect on transmittance is not that severe, meaning that although grain size is important, it is not everything. Evaluating the mechanical properties, we looked at the flexural strength and compared it with the phase fractions of the different materials. The phase fraction of the two 3Y materials are relatively comparable, whereas the flexural strength is higher for the 3Y material with lower binder concentration. We believe this to be related to residual pores in the material. So if you have less binder, you get less pores and slightly higher strength, as these pores can then somewhat weaken the material. Whereas with a higher binder content, you get a slightly lower strength. However, both or all of these values are well over 1000 megapascal, meaning that the strength is still really high. For the 4Y material, we see a slope down in the mechanical strength when we increase the sintering temperature, meaning that if you have a furnace that sinter at a too high temperature, you risk reducing the mechanical properties of your material. And finally, we see that for the 5Y, we have the lowest strength, although within the group, the variation of the strength is not significant. We also see that we have a considerable increase in the tetragonal prime phase and a reduction in the tetragonal phase, meaning that it's not only the phase fractions and the phase content, which is relevant to the mechanical strength, but also probably properties such as grain boundaries. So to summarize, it's important to be sure about your sintering temperature of your furnace. Generally, you should consider calibrating your furnace and keep an eye on this. When evaluating the phase fractions of yttrium-stabilized zirconia, we need to evaluate both the tetragonal prime, and the cubic phase at least, and perhaps even more phases, although then this again depends on the quality of your instrumentation. We found that the sintering temperature can affect your transmittance, although not in all cases, and it's also the same for the flexural strength, that flexural strength can be affected by the sintering temperature, but not in all cases. It is also important to consider binder content, that a higher binder content can reduce the flexural strength, although it does not affect transmittance in our study.